Norol-isa Pañares. So the next step in finding critical path is to compute the latest start time and latest finish time for each activity. We do this by making a backward pass through the network that is starting at the finish and working backward to the start. Backward pass is a procedure that moves from end of the network to the beginning of the network. It is used to determining the latest finish and start time. So to compute the latest time of general foundry, we start at the finish and work backward to the start. Since the project completion is 15 weeks, therefore the late finish time for the activities at the finish node H has to be 15. That is, H cannot be completed in longer than 15 weeks. So next, we obtain the latest start time by subtracting the activity time from the latest finish time. For H, the latest start time will be 15 minus 2 to give 13. So the latest finish for F and G will be 13. And for G, the latest start time will be 13 minus 5 to give 8. And for the latest start time for F will be 10 since we subtract the activity time which is 3. So this figure show the general founder's latest start time and latest finish time. So as you can see or notice that activity C has two successor or immediate predecessor, which is activity F and E. So their late start time each is 4 and 10 respectively. So we use the rule number 2, which the latest finish time is equal to smallest late start of the following activity. So sa dalawang activity na yan or immediate predecessor na activity C, saan yung mababa yung late start niya? 'Di ba si letter E or si activity E? So it means ang magagamit natin na late finish ni C is yung late start ni E. So therefore, ang late finish ni C will be 4. And to subtract its activity time, ang late start time niya is 2. Same with A and B. Ang si B, activity B, ang immediate predecessor niya is isa lang which is si D. So, ang late finish time niya is 4 and then subtract 3 kasi activity times to get 1. Same with E. Activity E. Ang late finish ni activity C is 2. So, minus activity time na 2, we get 0. Concept of slack in critical path assumption. When early start, late start, early finish, and late finish have been determined, it is simple matter to find the amount of slack time or the free time that each activity has. Slack time is the length of time an activity can be delayed without delaying the whole project. Mathematically, slack time is equal to late start minus early start, or slack is equal to late finish or early finish. So this table shows the summarization of general foundries early start, early finish, late start, and late finish and slack time activities. For activity A, it has 0 slack. Activity B has 1 slack. Activity C, it has 0 slack. Activity D, it has 1 slack. And activity E, it has 0 slack. And for F, it has 6 slacks. And activity G and H has 0 slack. Activity B, for example, has 1 week of slack time since late late start and late start minus early start, which is 1 minus 0 is equal to 1. Similarly, late finish minus early finish, which is 4 minus 3 is equal to 1. This means that it can be delayed up to 1 week without causing the project to run any longer than expected. On the other hand, activities A, C, E, G, and H has no slack time. This means that none of them can be delayed without delaying the entire project, and yan yung tinatawag na critical activities and are said to be on critical path. So this table shows the critical path of General Foundries project. As you can see, the total project completion time is 15 weeks. Is seen as the largest number in the early finish or late finish columns of table 12.3. Industrial manager call this as a boundary timetable. Probability of project completion. This probability of project completion is the expected value of completion time expected from the project. So critical path analysis is to determine the total project completion time, the critical path for the project, slack, early start, early finish, late start, and late finish for every project. PERT or Program Evaluation and Review Techniques, a network technique that allows 3 times estimates for each activity in a project. So, the critical path analysis help us determine that the founder's expected project completion time is 15 weeks. However, Harky knows that if the project is not complete in 16 weeks, General Foundry will be forced to close by environmental controller since hindi niya na-meet yung deadline. And also Harky is aware that there is a significant variation in the time estimate for several activities. Variation in activities that are on critical path can affect overall project completion. Possibly, it can delay it. This is one of occurrence that worries Hargy considerably. PERT uses the variance of critical path activities to help determine the variance of overall project. So if an activity times are statistically independent, the project variance is computed by summing the variances of the critical activities. Project variance rather is equal to summing variance of activities on critical path. So from table 12.2 we know that critical path activity is A, C, E, G, and H. And their variance is 4 all over 36, 4 all over 36, and E is 36 all over 36, G is 64 all over 36, and H is 4 all over 36. So, um, project variance, like what I've said a while ago, is summing the uh, all project variance, summing all the variance of critical activities. So, with a total of 112 all over 36 or equal to 3.111. In this figure, it showed the probability distribution for project completion times. So the standard deviation is equal to 1.76 weeks and the expected completion time is 15 weeks. We all know that the standard deviation is just the square root of the variance. So project standard deviation is equal to a square root of project variance. So i-apply na natin yung project variation ng General Foundries project. So, 3.111 square root is equal to 1.76. And PERT has two assumptions. Number one is activity times are independent. Number two, total project completion time follows a normal probability distribution. So with these assumptions, the bell-shaped curve shown in figure 12.7 can be used to represent project completion dates. It is also mean that there is a 50% chance that the entire project will be complete less than the expected 15 weeks and a 50% chance that it will be exist in 15 weeks. And to find the probability for Harky that his project will be finished on or before the 16-week deadline, he needs to determine the appropriate area under the normal curve. That is normal equation can be applied as follows.
Standard normal equation Z is equal to due date minus expected date of completion all over project variance. So 16 weeks minus 15 weeks all over 1.76 weeks is equal to 0.57.
Where Z is the number of standard deviation, the due date or target date lies from the means or expected date. Areas under the standard normal curve. In this table, we are referring to find the 0.57, which is yung probability niya. So, ang probability niya is 0.71566 kasi nag-meet si 0.5 at saka si 0.07 sa 71, 56, and 6, which is 71.6% chance that the pollution control equipment can be put in place in 16 weeks or less. This is shown in figure 12.8. So, ito na yung probability niya. Standard deviation, which is 0.57. Expected time is 15 weeks. And the probability is 71.6% time duration. Sensitivity analysis and project management is the time required to complete an activity during any project may differ from projected or expected time. As previous discussion, if the activity is on the critical path, the total project completion time will change. There is an impact on the earliest start, earliest finish, latest start, latest finish, and slack times for other activities in addition to the project completion time. The exact impact is determined by the interaction of the various activities. Predecessor activity is one that must be completed before the given activity can be started. In previous section, we define an immediate predecessor activity as an activity that comes immediately before a given activity. So consider that activity G rather, installation pollution device for activities A, B, C, D, and E. All of this activity must be completed before activity G can be started. And successor activity is an activity that can be started only after the given activity is finished. Consider activity H is the only successor activity for activity G. Parallel activity is an activity that does not directly depend on the given activity. So for example, in the network for General Foundry, consider activity G is a parallel activity niya is activity F since hindi siya directly nagdepend sa given activity. So this table shows the impact of an increase or decrease in an activity time for a critical path activity. So if the time it takes to complete activity G increases, there will be an increases in the early start, early finish, latest start, and latest finish time for all successor activities. Because these activities follow activity G, this time they also increase. Because slack time is equal to latest finish time minus the earliest finish time or the latest start time minus earliest time, there will be no changes in the slack for successor activities. Because activity G is on the critical path, an increase in activity time will increase the total project completion time. This would mean that the latest finish, latest start, and slack time will also increase for all parallel activities.
So next topic is the PERT/cost. PERT is good for planning project, but it is not considered the very important factor, which is the cost factor. PERT/cost is a modification of PERT that allows a manager to plan, schedule, monitor, and control costs as well as time. So if you want to include the cost factor for planning your projects, you can use the PERT/cost. These are the steps of budgeting process. First, you need to know how much each activity costs for you. Then you can sum or add them up to get the total budget available. Next, if you're going to do a bigger project, several activities can be combined into large work packages. So, ang work package is for example, yung large project na yan, hahatiin natin siya into 3 parts. Then, yung 3 parts na yun yung work package. Then, you can check the whole budget cost per week, how much you can spend and how much you have spent over it. And lastly, you can also find out whether you have spent appropriately or if you're going according to the time or date or not. So budgeting cost could be done according to Gantt chart. So ito yung Gantt chart. As we can see, activity A starts from week 1 and 2, and activity B, week 1, 2, and 3, and so on. So the next table is much more clear. We can see that activity A, then earliest start time, latest start time, expected time, total budgeted cost, and budgeted cost per week. So itong 22,000 na total budgeted cost is allocated for activity A. So activity A takes 2 weeks to be completed. So to get the budgeted cost per week, kailangan lang nating i-divide ang total budgeted cost sa expected time. So 22,000 divided by 2, so 11,000 ang cost per week. Same sa activity B, 30,000 divided by 3, so 10,000 ang budget cost per week. So you can also calculate the budgeted cost using the earliest start time. So activity A will start in the first 2 weeks. So 11,000, 11,000 din sa second week, total of 22,000. So sa activity B, it will start in the first 3 weeks, so 10,000, total of 30,000, and so on. So next, sa total per week, so sa week 1, total of 21,000, then week 2, total of 21,000, and so on. So sa total to date is i-add lang natin yung total per week. So first week, we have 21,000, then second week, add lang natin tong dalawa, we have 42,000, third week, add lang natin tong tatlo, 65,000, and so on. And you can also do the same thing for the latest start time technique. So ito yung latest start time techniques. We can see same lang sa earliest start time technique kanina. Same result. Yeah. So here we can see that if an activity is not started until its latest start time, there is no slack available. So if there is any delay, it will affect the whole project. So you should not aim to start every project or activity in the latest start time. Next is monitoring and controlling project cost. We want to plan and control the project cost, which is important, so that it doesn't cross the amount that has been allocated for each activities. So ito yun, cost overruns are kept to a minimum. So you can check the value of work completed by multiplying the percentage of work completed and the total activity budget. Then you can find the activity difference by subtracting the actual cost and value of work completed. So if any activity difference is negative, there is a cost underrun. But if the activity difference is positive, there has been a cost overrun or you have overspent. Like in this table, activity A. For activity A, we have a total budget cost of 22,000. But the actual cost is only 20,000. So, ang formula natin for activity difference is actual cost minus value of work completed. So, 20,000 minus 22,000 is equal to negative 2,000. So, add lang natin lahat yan. And since positive yung activity difference, it is considered as an overrun.
My name is Matabalao, and today, for my part in Chapter 12, is what is project crashing. So, at times, projects have deadlines that may be impossible to meet using the normal procedures for completion of the project. However, by using overtime, working weekends, hiring extra workers, or using extra equipment, it may be possible to finish a project in less time than is normally required. However, the cost of the project will usually increase as a result. When CPM was developed, the possibility of reducing the project completion time was recognized. This process is called crashing. So here we can see that project crashing, by definition, is the process wherein the completion time of a project is reduced. In other words, it is the shortening of a project. When crashing a project, the normal time of each activity is used to find the critical path. The normal cost, then, is the cost for completing the activity using normal procedures. If the deadline is before the normal completion time, then we can say that the crash time is the shortest possible activity time and requires the use of additional resources. The crash cost is the price of completing the activity in an earlier than normal time. There are 4 steps in project crashing with CPM. First is find the normal critical path and identify the critical activities. Then, we should compute the crash cost per week or other time period for all activities in the network. This process uses the following formula. Here we can see that the crash cost per time period is equal to crash cost minus normal cost over the normal time minus the crash time. The third step is select the activity on the critical path with the smallest crash cost per week. Crash this activity to the maximum extent possible or to the point at which your desired deadline has been reached. Check to be sure that the critical path you are crashing is still critical. Often, a reduction in activity time along the critical path causes a non-critical path or paths to become critical. If the critical path is the longest path through the network, return to step 3. If not, find the new critical path and return to step 3. Here we can see an example of computing the crash cost per week for activity B. We can see that the crash cost is $34,000 and the normal cost is $30,000. And the crash time is one week and the normal time is 3 weeks. So if we were to compute the crash cost per week, it would be crash cost per week is equal to crash cost minus normal cost over normal time minus crash time, which is $34,000 minus $30,000 over 3 minus 1, giving us $4,000 per 2 weeks or $2,000 per week. Here we have the General Foundry example. Suppose that General Foundry had been given 14 weeks instead of 16 weeks to install the new pollution control equipment or face a court-ordered shutdown. As you recall, the length of Lester Harkey's critical path was 15 weeks. What can he do? We see that Harkey cannot possibly meet the deadline unless he is able to shorten some of the activity times. General Foundry's normal and crash times and normal and crash costs are shown in Table 12.9. Note, for example, that Activity B's normal time is 3 weeks and its crash time is 1 week. This means that the activity can be shortened by 2 weeks if extra resources are provided. The normal cost is $30,000 and the crash cost is $34,000. This implies that crashing Activity B will cost General Foundry an additional $4,000. Crash costs are assumed to be linear. And as shown in the figure I showed you before, Activity B's crash cost per week is $2,000. Crash costs for all the other activities can be computed in a similar fashion. Then, steps 3 and 4 can be applied to reduce the project's completion time. Here we can see that activities A, C, and E are on the critical path and each have a minimum crash cost per week of $1,000. Harkey can crash activity A by 1 week to reduce the project completion time to 14 weeks. The cost is an additional $1,000. At this stage, there are 2 critical paths. The original critical path consists of activities A, C, E, G, and H, with a completion time of 14 weeks. The new critical path consists of activities B, D, G, and H, also with a total completion time of 14 weeks. Any further crashing must be done to both critical paths. For example, if Harkey wants to reduce the project completion time by an additional 2 weeks, both paths must be reduced. This can be done by reducing activity G, which is on both critical paths, by 2 weeks for an additional of $2,000 per week. The total completion time would be 12 weeks, and the total crashing cost would be $5,000. $1,000 to reduce activity A by 1 week and $4,000 to reduce activity G by 2 weeks. For small networks such as general foundries, it is possible to use the four-step procedure to find the least cost of reducing the project completion dates. For larger networks, however, this approach is difficult and impractical, and more sophisticated techniques such as linear programming must be employed. So what if Harky wants to reduce the project completion time by an additional 2 weeks, giving us 12 weeks to finish the project? Then we can say we need to use the project crashing with linear programming. There are 4 steps in project crashing using linear programming. First is define decision variables for the linear program. Next, determine the objective function. Next, determine crash constraints, and then determine event constraints. First step is defining the decision variables. If x is the earliest finish time for an activity, then we can say that x sub a is the earliest finish time for activity A, x sub b is for activity B, and so on until activity H. Then we have x sub start, which is the start time for a project, usually 0. And then the x sub finish is the earliest finish time for the project. Y is defined as the number of weeks that each activity is crashed. Y sub A is the number of weeks we decide to crash the activity A. Y sub B is for activity B, and so on up to Y sub H. Next, we need to determine the objective function. Since the objective is to minimize the cost of crashing the total project, our linear programming objective function is minimize crash cost is equal to 1000 y sub A plus 2000 y sub B plus 1000 y sub C plus 1000 y sub D plus 1000 y sub E plus 500 y sub F plus 2000 y sub G plus 3000 y sub H. These coefficients beside the y sub A until y sub H were taken from the 6th column of table 12.9, which we can see is a crash cost per week in dollars. Next is to determine the crash constraints. Constraints are required to ensure that each activity is not crashed more than its maximum allowable crash time. The maximum for each y variable is the difference between the normal time and the crash time, also from table 12.9. Here we can see that the time in weeks has a difference between the normal and the crash time. For activity A, it is 2 minus 1, which we can see is y sub A is should be less than or equal to 1, and so on until y sub H. We just need to subtract the crash time from the normal time to get the constraints. When determining the crash constraints, there is also the project completion constraint, which specifies that the last event must take place before the project deadline date. If our case project must be crashed down to 12 weeks, then X sub finish should be less than or equal to 12, which is the number of weeks. The final set of constraints describes the structure of the network. Every activity will have one constraint for each of its predecessors. The form of each of these constraints is earliest finish time is greater than or equal to earliest finish time for predecessor plus activity time. Here we can see that the activity time is t minus y. This is to say that the normal activity time minus the time saved by crashing. The activity time is given as t minus y, or the normal activity time minus the time saved by crashing, and we know that earliest finishing time is equal to ES plus activity time, and ES is equal to the largest earliest finish of the predecessors. Here are the event constraints for each of the activities. We begin by setting the start of the project time to 0, so x sub start is equal to 0. For activity A, we have x sub A is greater than or equal to x sub start plus 2 minus ya. These values are also taken from the table 12.9. And when we simplify it by isolating the only constant, x sub A is equal to x sub start plus y sub A is greater than or equal to 2. The same should be done for the following activities. So for x sub b is greater than or equal to x sub start plus 3 minus y sub b. This would give us x sub b minus x sub start plus y sub b is greater than or equal to 3. This is because both activity A and activity B are preceded by the starting time. Then for activity C, we have x sub c is greater than or equal to x sub a plus 2 minus y sub c. Or we can say x sub c is minus x sub a plus y sub c is greater than or equal to 2. This is because activity C is preceded by A. For activity D, we have the same process. So x sub d is greater than or equal to x sub d plus 4 minus y sub d. This will give us x sub d minus x sub b plus y sub d is greater than or equal to 4. This is also because d is preceded by activity B. Then for activity E, the same can be done except the preceding activity would be C. So x sub E is greater than or equal to x sub C plus 4 minus y sub E. For activity F, the same should be done. However, for activity G, we need two constraints since there are two predecessors. These predecessors are activity D and activity E. So the first constraint is x sub G is greater than or equal to x sub D plus 5 minus y sub G. This would give us x sub G minus x sub D plus y sub G is greater than or equal to 5. The second constraint, which is preceded by E, is x sub G is greater than or equal to x sub E plus 5 minus y sub G. Or we can say x sub G minus x sub E plus y sub G is greater than or equal to 5. The same is also done for activity H, with H's predecessors being activity F and activity G. Both have the same time, which is 2. So x sub h is greater than x sub f plus 2 minus y sub h. Or we can say x sub h minus x sub f plus y sub h is greater than or equal to 2. The second constraint is x sub h is greater than or equal to x sub g plus 2 minus y sub h, or x sub h minus x sub g plus y sub h is greater than or equal to 2. Since h is the last activity, to indicate the project is finished when activity h is finished, we have x sub finish is greater than or equal to x sub h. After adding non-negativity constraints, this LP problem can be solved for the optimal y values. This can be done with QM for Windows or XLQM. Program 12.2 provides the XLQM solution to this problem. So when finding y, activity A is crashed by 1 week and activity G is crashed by 2 weeks. And the total cost of crashing would be $5,000, as was said earlier. The formula in cell T4 is copied down column T from T5 to T25. Here are the other topics in project management. First is sub-projects. For extremely large projects, an activity may be made of several smaller sub-activities. Each activity might be viewed as a smaller project or sub-project of the original project. The person in charge of the activity might wish to create a PERT or CPM chart for managing this sub-project. Many software packages have the ability to include several levels of sub-projects. Next is milestones. Major events in a project are often referred to as milestones. These are often reflected in Gantt charts and PERT charts to highlight the importance of reaching these events. Next is resource leveling. In addition to managing the time and cost involved in a project, a manager must also be concerned with the resources used in a project. These resources might be equipment or people. In planning a project, and often as part of the work breakdown structure, a manager must identify which resources are needed with each activity. For example, in a construction project, there may be several activities requiring the use of heavy equipment such as crane. If the construction company has only one such crane, then conflicts will occur if two activities requiring the use of this crane are scheduled for the same day. To alleviate problems such as this, resource leveling is employed. This means that one or more activities are moved from the earliest start time to another time, no later than the latest start time, so that the resource utilization is more evenly distributed over time. If the resources are construction crews, this is very beneficial in that the crews are kept busy and overtime is minimized. Last is the software. There are numerous project management software packages on the market for both mainframe computers and personal computers. They can be used to develop budget schedules, automatically adjust future start times based on the actual start times for prior activities, and level the resource utilization. It helps the management make better decisions and keep track of things that would otherwise be unmanageable.